Hello, everyone. It's Mr. Slomka here, and we're going to start talking about Chapter 6 this week. And we're going to start off with Section 6.1, which is on a couple of theorems that are going to be about bisectors. We're going to have angle bisectors and perpendicular bisectors for segments. Now, the majority of Chapter 6 is on some new and interesting ideas that have to do with triangles, but Chapter 6, Section 1 is going to focus on some of those elements that we're going to then apply to triangles. So we're really going to be focusing on some lines, but then we're going to take it a little bit further and create some triangles as we go. So let's start off by talking about perpendicular bisectors. So perpendicular bisectors is going to be a line that is going to split another line perfectly in half, and it's going to create a 90-degree angle, which are all things that we know. But we're going to add on an extra piece to that, which is going to be called the perpendicular bisector theorem. And the perpendicular bisector theorem is going to state if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So what we are talking about right here is we're talking about our segment AB, and then what we're going to do is we're going to have a perpendicular bisector that is going to run right through here, which is going to be CP. And you can see that it's perpendicular, and you can see that it's bisecting by creating these two smaller congruent sections. Now, the part that is going to be the interesting part, the new part, is going to be then looking at the distances that we have from C to A and C to B. Now, if you take a look right here, it says if line CP is the perpendicular bisector of segment AB, then CA is equal to CB. Those two segments that are formed by reaching out from our perpendicular bisector back down to our segment are going to be the same length. And because they're the same length, we get to mark them with those tick marks. Now, this exact theorem also works backwards. If we start off with this piece of information and we go back, we can get to these pieces of information that we are talking about here. That's called a converse. And that converse is stated very clearly for us right here. So if we start off with a point that is equidistant from the endpoints of a segment, then that point is on the perpendicular bisector of that segment. So you'll notice that this picture right down here is almost identical to the one that's above it, but the starting information is different. If you notice, I'm starting off by giving you these tick marks on either side, and the part that I'm going to add now is the piece about the perpendicular bisector. So once you've added in the information, both of the drawings end up looking the same, but the starting place was different. One started off with the information about the perpendicular bisector, and the other one ended with the information about the perpendicular bisector. So that is a little bit backwards. Let's see if we can take those two theorems and kind of use them. So we have a couple of example problems right here. I'll do one and you can do one. So example one right here says we have line AC, which you see running right through the middle right here. And it is the perpendicular bisector of segment BD, which we have running vertically. So we know already that they're going to form a 90-degree angle, and we're going to have our congruent sides. What I want to do is I want to find AD. Now, since A right here is on the perpendicular bisector, that means that these two segments that we are taking a look at right here are equidistant. So I can say that they are the exact same length. That also means that I can set these two expressions equal to each other. So we can take our 7x minus 6, and we can set it equal to our 4x. Once you've set them equal to each other, now you have an equation that you can solve using your algebra skills. And so I'm going to do that. I'm going to bring my 4x over here with my 7x by subtracting it. And I'm doing this because I like positive numbers, and so that's going to work out well for me. Then I'm going to bring my 6 over to the other side, just so we can isolate that x variable. And I'm using opposite operations. And I'm going to get 3x is equal to 6. And then lastly, I'm going to divide. You can do this work a bunch of different ways, so you can pick the way that makes you feel most comfortable. But this is the way that I like to do it right here. Okay, now that works out pretty nicely, but we're certainly not done. If you go back to the question, it doesn't say find x, it says find AD. So we need to take this another step further. So let's see if we can now take that information that we just collected about x and use it to find AD. Well, on our drawing, AD is labeled as 4x. And I also know now that x is equal to 2. So that means that if I plug a 2 in there, then I should be able to get my distance for AD, and I get 8. That's the final answer. Now, if you wanted to check this, which is always a fantastic idea, remember that our second segment should have the exact same length. So if you take another 2 and plug it in there, you should get the identical value. 7 times 2 is 14, but 14 minus 6 is still 8. So that works out wonderful, and you still get the same answer. All right, it is your turn. I now want you to see if you can find the length of the segment CA. So we are dealing with another perpendicular bisector right here. Now segment CA is a pretty long one. So if you take a look right here, I've marked it off with my question mark. And what I'm going to do is I'm going to do some similar work. I already had the tick marks on here, which is pretty nice for you. That states that 2x plus 4 is congruent to 4x. So I've set those pieces equal to each other in an equation, and I've solved for x. Now CA is going to be a combination. It is both a combination of CD and also DA. So I've written out CD plus DA here. And then I've used my 2x plus 4 and my 4x to put them both in there. Not surprisingly, I get a distance of 8 for both of those. And then when I add those 8s together, I get a total distance of 16. Now, if you didn't do your work this exact same way, that's fine, because there's a bunch of different ways you could do it algebraically. But the goal here is to get the exact same answer that I got, which is 16. Make sure that you do not stop at 2. It is always tempting to stop before you're done if you're not paying a close attention to what the question is asking for. And in this case, it's asking for CA, not just X. Example number 2 is a little bit different. This one's a little bit more of an analysis problem and less of a solving one. It says, tell whether the information in the diagram allows you to conclude that C is on the perpendicular bisector of AB, and explain using a theorem. So what we have right here is we've got the point C. And the major thing that I want to know about is we have a perpendicular bisector, ED, right here. You can see that's perpendicular and then it's bisecting. My question for you is, if I extend this line right here, will it actually pass through C, or will it pass maybe a little bit to the left or a little bit to the right? And that can be hard to say. And you certainly can't just look at the drawing and make a choice about that. That's not very good. So what we need to do is we need to make sure that we've got some good rules or some reasons to back that up. So in my opinion, I'm going to say yes. I'm going to say that yes, C is going to exist on the perpendicular bisector. And the main reason for that is because not only can I see that I have a perpendicular bisector, but I can also see that C is equidistant from A and B. So that is an important piece right there. And the big theorem that I am drawing on here that is allowing me to state that this is going to be a perpendicular bisector is going to be the converse to the perpendicular bisector. Let's go back and take a look at that real quick. So for the converse, once again, if you start off with the idea of equidistance, then that tells you that the point has got to lie on the perpendicular bisector. And that's certainly what we have. We had a lot of information in this drawing right here about perpendiculars and bisectors and equidistance, and that allowed us to say, yes, C is going to exist on that perpendicular bisector. It's your turn. I'm going to give you far less information, but ask you to see if you can come up with a similar type of conclusion, either yes or no. Even though your drawing goes with very little, it is the same result. You only really need to start off with equidistance. You don't really need anything else. So if there was a perpendicular bisector that was drawn in for this picture, it would pass through point C. So if I create my own perpendicular bisector, it will pass directly through point C, and it will look fantastic. So there you go. All right, next piece. In order to make sure that we are going to be clear on our next 2 theorems, because we've got 2 more to take a look at, there is something that I want to remind you about, and it's right down here. I want you to recall that the distance from a point to a line is the length of the shortest segment from the point to the line. By that, what I mean is from point A to this line that we could call maybe L, there are lots of distances that we could measure. We could measure this distance right here, or we could measure this distance right here, and they all represent the distance from the point to the line. But they're inconsistent. They're all different distances. So whenever we're talking about the distance from a point to a line, we're always referring to one specific one. And that one specific distance that we're referring to is the shortest one. And that one will always look like this. Okay, so then the question becomes, how do you know that it's the shortest distance? And the way that you know it's the shortest distance is because it's perpendicular. It will form a 90-degree angle. So when I say shortest, I also mean perpendicular. This is not a new idea. We've seen this a couple of times in our classes. So when I say things like supplementary, when I say things like linear pair, and when I say things like 180 degrees, I want you to understand that I'm talking about the exact same thing over and over and over again. And the same thing is happening here. When I'm talking about the shortest distance, I'm also talking about the perpendicular distance. So both of these are very interchangeable. So I should be able to refer to each of them, and you should know that I'm also referring to the other one at the same time. So this is an important fact. We've seen it before, but I wanted to remind you about it because we are about to talk about the angle bisector theorem. So for our angle bisector theorem, what we are going to do here is we're going to have an angle. If a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. Okay, so here's a picture right here. And what you can see here is we've got our nice angle, which we could call BAC, that angle right there. And then we've got this ray, AD, that is coming up through the middle. And it has split our angle perfectly into two smaller equivalently sized angles. Now let's talk about the point D. For the point D, there is distances that you can measure out to either side of the angle, and these measurements need to be equidistant. They need to be the same. Okay, so now just like we were talking about before, when you measure these distances, you could go straight across or you could go up on an angle or down on an angle. How do you determine what is the correct distance? And it's always going to be the shortest one, the perpendicular one. Okay, so here's our if-then statement. If a ray AD bisects angle BAC and DB is perpendicular to AB and DC is perpendicular to AC, those are those two 90-degree angles that we have to have, then we can make the statement that DB is equal to DC. Perfect. We've got them marked over here and we've got them in our if-then statement. And just to follow that up, once again, in geometry, distance means the shortest length between two objects, aka the perpendicular length between two objects. So we're going to once again use those interchangeably. Okay, so just like on the front side with the perpendicular bisector, the converse of the angle bisector exists and we can use it. The converse of the angle bisector is just going to work backwards. So if you're going to start off with a point that is in the interior of an angle and is already equidistant to two other points, then it is going to lie on the bisector of the angle. So we're going to end with the bisector instead of starting with it. Okay, so let's take a look at what we've got right here. So once again, we've got our perpendicular lines, which are going to create our 90-degree angles. You can see those. You can also see that our distances are going to be a matched set, and those are marked off with our tick marks. And that means that AB, or ray AD, is going to bisect the angle. So we can finish off by marking off our two angles that we have right here and right here. Okay, so here's an important point, and I want to make sure that this is clear because it can be subtle if you're just looking at the note sheet. The important thing it says right here, it says, so what always has to be true no matter what you are doing, whether you're doing the converse or not. And the thing that I'm noticing about both of these theorems, and specifically when you look at the if-then statements, it becomes very clear, is that when you're looking at both of these, you have to start off with this concept of perpendicular lines. If you don't have those perpendicular lines, then you won't be able to do much. So this angle bisector is really, really focused on this idea of the shortest length and these perpendicular lengths, and so you have to have them. It is part of the if statement both times, regardless of whether you're doing the regular theorem or the converse. So that is a really, really clear and important piece, so you need to make sure you have it. So if you don't have those 90-degree angles showing up, you're up the river. You got to get those first, and then you can use these theorems, but you can't use them until after you've got the 90-degree angles. Let's try out some of these problems. So example number 3 right here is going to be another one just where you're finding the measure. And so I'm looking to see if I can find the measure of CBE. So CBE is going to be this smaller angle right over here. And it looks like it hasn't been bisected, but it was formed by the bisector. So I'm guessing that we started off with angle CBD right here, and then it got bisected by ray BE. Now, what I'm noticing about the bisector is that if we go up here to point E, I have two equidistances that are perpendicular. So that tells me that I should have an angle bisector. So CBE should match DBE. And that means that the measure of angle CBE is going to be 31 degrees. That is going to be a match set with the left side and with the right side. This is from the converse. The reason that I know it's the converse of the bisector is because I'm starting off with the perpendicular angles and the equidistance. And then I'm ending my time and I'm getting my conclusion from the actual angle bisector. Let's take a look at angle 4, or example 4, I should say. Example 4 is right here, and this one is a little bit of a loose one, so we're going to do a little extra work with this one. It says, for what value of x does P lie on the bisector of angle J? So right now, we don't have an angle bisector, but we're going to build one. So that's what we're going to work on right now. So we have our variables again. So we're going to be doing some solving, but we're going to do a couple of things. So thing number one is what we really need to do is we really need to make sure we've got 90-degree angles. Okay. So that's something that we're going to add in here. 9 times out of 10, they should be there for you already. And if they're not there, that should be a red flag. But this one right here, since we're building a perpendicular bisector, we're going to put those on there. Okay. Next, you can draw in your bisector if you want. I'm going to choose to do that, but that's an option that you can choose to do or not do. And basically what this is going to do is this is going to create the opportunity. If we want the bisector to exist down here, we need equidistance up here. So we're going to create that equidistance by setting our two distances equal to each other. Oops. So I've got my x plus 1 from the top portion, and I've got my 2x minus 5 from the bottom portion. I've set them equal to each other because they should be the same. Okay, so let's see if we can solve. I'm going to get my x's together because I always like to collect my x's first. It makes me feel comfortable, and that's the way I like to do it. Then I'm going to move my constant terms around by moving my 5. And I get my x value, which is going to be 6. Okay, so now this question is just asking about x values. It does not ask you to find the distance. And so you don't have to if you don't want to. And so you're good to go. Now, if you do want to check your work, you can find that distance pretty quickly and easily by taking your 6 and plugging in here. 6 plus 1 is 7. 2 times 6 is 12, but minus 5, you're back to 7. Let's try example number 5. So for example number 5, this one right here says that they want you to find the value of x, and it has got all of the great markings in there. I want you to try out example number 5 on your own. All right, so it's got the 90-degree angles. And it's got the equidistance. So everything is set up and ready to go, which means we can now take our two angles, which are equivalent because they have been bisected, and set them equal to each other. When you solve this one, you just have to find x. So we're going to get our x value of 10, and we will be done. Example number 6 is going to be a little bit different. So example number 6 is a bit of a throwback. It's a review from Algebra 1. Not the most critical example on the whole sheet, but a good one to look back at. This one is actually asking you to create a perpendicular bisector for the segment DE. So we've got our 2 points D and E. D is at 5, -1, and E is at -11, 3. I've roughly graphed them out so I can kind of show you. And you don't have to draw them if you don't want to, but you do need to make sure you remember some of the work. What I'm going to do right here is I'm going to be trying to create, once again, a perpendicular bisector, and that should split my segment in half, and it should do it by creating a 90-degree angle. So I'm looking for a line that is going to roughly kind of sort of look like this. It should have a positive slope, and it should intersect my y-axis somewhere up high. So let's see if we can create that. So I'm going to do a couple of things. First thing I want to do is I want to locate this point right here. That's going to be an important point. That point is called the midpoint. Now we have a midpoint formula, which works really, really well. So I'm going to start off with my midpoint formula. And the way the midpoint formula works is you're going to average your x's and average your y's. So I'm going to take my two x values, which are 5 and -11, and I'm going to average them by adding them together and dividing by 2. I'm going to do the same thing with my y values. I'm going to take both of the y values, which is -1 and 3, and I'm going to average them by taking them and adding them together and dividing by 2. This is going to give me the location of the point that is smack dab in the middle of D and E. When you do the work, the addition and the division, you are going to end up with the point -3, 1. Now it seems pretty reasonable. If I look at my drawing, it looks like it might be about -3 units over and 1 unit up. So I'm feeling good about that point right there. Okay, next. The other portion that I'm really interested in is the slope of this line. And so I want to see if I can calculate some slope. Now I'm going to calculate slope using rise over run, or y2 minus y1 over x2 minus x1. So there's some y values, and then here are some x values. And when I calculate slope, I am going to get 4 over, 16. And that reduces, and that's going to reduce down to -1/4. Now that's not exactly the perfect slope. That's actually the slope of this red line that I have right here of the segment DE. That's not the one that I want. I want the slope of the line that is perpendicular. Luckily for us, there is a really quick rule that lets you create a perpendicular slope. And that general rule is that you need to have an opposite reciprocal slope, which means that whatever is negative becomes positive, and whatever was on the bottom goes to the top, and what was on the top goes to the bottom. That's called a reciprocal. So my slope that I'm really after is going to be positive 4/1, or if you'd like, just 4. Okay, so now how do I take this great point and this great slope and make an equation of a line? Well, the easiest way to do that would be actually to create a point slope equation. And to do that, your basic technique right here is going to be y minus y1 equals mx minus x1. This is old algebra stuff that you may or may not remember. Once again, not the most popular example on the whole page. If you want to fill this in really quickly, you can. So what I'm going to do here is I'm going to take all of the pieces that I collected and put them in their correct spots. Let's start with slope. My slope is 4, and that's going to replace my m variable. Next, let's do our point. My point right here is -3. That is an x value, so I'm going to put it in with my x, and I am going to list it as the opposite operation. See that minus sign right there, and that minus sign right there, minus a negative makes a positive. I'm going to do the same thing with my y value. My y value is 1. I'm going to use that over here with my y variable, and that minus sign right there needs to be used. So our final equation looks like this guy right there. That's a point slope equation, and that guy is of the perpendicular bisector. Now, if you are a big slope intercept form fan, you can do it that way as well, but it's not as easy. So it takes a little bit longer, and you might not like it as much. Here's the same equation in slope intercept form. All right, last example that we have right here. So for our last example, what I want to do is I want to do another kind of analysis. We have a picture right here with no numbers on it, and we need to decide if we think that BD bisects the angle ABC. So we've got our ray right here, and we have our angle, and we want to know, is it actually a bisector? Now, everything is looking pretty good to begin with. I do have my perpendicular angles, but I don't have my equidistance. And because of that, that means that I'm going to say no, that's not a good perpendicular bisector. And what I would really need is I would really need DA to be equivalent to DC. And then I could use the converse of the angle bisector, and I could get the job done. All right, your turn. See if you can do letter B on your own. See if you can come up with a similar type of conclusion. Our picture has the perpendicular angles and it has the equidistance. So you get to say yes. Yes, the converse of the angle bisector theorem is going to allow you to state that we have an angle bisector on our hands. Okay, that is it and that is all. It is time to move on to some practice.